Alright, time for another draft science video presentation. Okay, today will be a subject video, relativity. Now, I've done a video on gravity, the alternative explanation, and so go check that out if you're so inclined, if you really care to understand that there can be a simpler explanation than Einstein's theory. I say Einstein's theory with some dissidence, because what people say Einstein said and what Einstein said aren't necessarily the same thing. I don't know if Einstein really was overtly destroying the concept of absolute velocity as being a reality, that things had actual positions in space and were moving in actual directions and all of that. And certainly all the, how much time is a measure of perception rather than a measure of anything real. When you perceive something to have happened, it doesn't have much to do with the fact that you could model what actually happened, and that two spontaneous events do not become not spontaneous. I mean, not spontaneous, instantaneous, no. Simultaneous. Two simultaneous events don't change because you changed your perspective and where you're viewing them. The fact that the information takes time to get to you doesn't change the fact that the thing happened at a certain time. It will affect you if it's a bullet from a gun and it's going to hit you. It's relevant that it takes time. It's a fact, but it doesn't mean it didn't happen when it happened. It's just, what I would argue is just kind of an understanding you can have that whatever this relative thing is, it doesn't break the fact that things are in places in the universe and they're not in more than one place because there's somebody perceiving it, and therefore the perceiver gets to decide where it really is. That's not how it works. Alright, so there are things in the universe that are not moving, and there are things that are moving, you could argue. And the fastest you can move is the speed of light. And light is created by a mechanism, things that are moving, atomic bits, pieces of matter. Light's a force, and that means but it's made out of something, I would argue. And it's always in some place, this force. Energy does transfer from one place to another. It doesn't transfer from one time to another. It doesn't do any of that stuff. Alright, so let's go through some of the basics of why Einstein was considered a relevant theory. Now, the one that I believe came first, and the one that is kind of showy, is the idea that he accounted for the slight variation in the orbit of Mercury. And so all the planets came out pretty good with Newton physics. Now, pretty good is okay, but it wasn't exactly perfect. So they sort of imply that there was an amount of perfection in everything else, and that Mercury was the only one off. So you have the idea of the sun, and the idea is that Mercury's doing this kind of thing. It's like each orbit's a bit not the same as the previous orbit, so it's precessing in its orbit, and that the other planets not so much. And that's the point, is not so much. Now, what Newton didn't know for a certainty was the speed of light, okay, and he didn't know that gravity, okay, was something that took time to affect something. So whatever influence things were going to have on each other, that also moved the speed of light, or the speed of force. That the force, see, this is another reason to doubt all this stuff, is that the speed of all the fast stuff is the same speed. It's the speed of all the forces, the speed of light. So you have the speed of gravity, okay. So if you take those two things into account, you change where we observe things. You understand your observation is wrong, and you understand that the effect of the gravity is in a different position. So first you get the right position by having the speed of light, and then you get the understanding that that right position is also a little bit off because gravity took time to get to the place it was going to affect something. And so you take those two things and then just understand what I'd say is a kind of a simple thing that, again, Newton didn't think it would be significant enough, I imagine, or whatever. But the idea that the sun has a center of gravity and you can't measure its center of gravity, just like you really can't measure where the center of gravity at any one moment in, say, Jupiter. Okay, I mean, Jupiter's out here somewhere. It has its center of gravity is what you're really measuring when you're measuring its position. And the fact is depending on where Saturn and Uranus and these other planets are, the center of gravity can be a little different than what you're observing, because the mass of the object is not consistent. There's light stuff and then heavy stuff, and the heavy stuff can actually move around inside the light stuff without changing the actual position of the object. So likewise the sun, I mean, it's a pretty small sun, but I'll have to deal with, just make it a little bigger for the sake of the argument. So we have the sun, not very round, but you'll get the idea. So the idea would be is that we can look at the sun and say the sun is here, but that here means that this is its center of gravity, would be the center of this whole object. But the truth is that the mass of the sun is also thickens as you go deeper, and the true center of the sun can be precessing. That is, the center of the sun's gravity is moving around and swirling around depending on where all these planets are and everything else. Its center of gravity moves, changes position, and so it's not in one place. The sun isn't always in one place relative to everything else. Now obviously the whole thing is moving through space in some direction, and that's another thing to understand, but regardless, the relative perception is this is the center of gravity here because the sun looks like it's here. But if you measure the actual center of gravity, you'd find that it moves from here to over 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 here. And the simple explanation for why Mercury is screwed up is because Mercury is very close to the sun relative to the other planets, so they're much further away. So that precession, that movement, is, as a measure of distance, a larger percentage of the distance between the sun and Mercury than it is the distance between, say, the Earth and the sun. That tiny precession becomes a tiny amount of difference in the distance, and therefore has a minor effect. So the reason why Mercury precesses is because the sun precesses. The center of the sun's gravity is not some solid thing. So if you understand that, you can understand why. So there's a counter explanation that I think is viable, and maybe Einstein's equations are actually saying that. They're just saying it in such a complex way that you can't see that that's what it's saying. But it's kind of a simple idea. All right, now to the... So that's... Yes, it impressed the world, or impressed at least scientists, that Einstein's mathematics did account for it. Now the trick is that everybody said things like, well, nobody understands those equations, so what good is it, right? If only two people understand Einstein, like Eddington made a joke about this, Einstein's theory, and I believe this was before the light experiment, the eclipse. And he quipped, who's the third person? Somebody asked him, I hear only 3 people understand. And he says, well, I know 2, me and Einstein. Who's the third guy? So, that's how complex the math is. That, there wasn't too many people on Earth who were willing to go through the process of learning how to do Einstein's calculation to even verify that it was what it was doing and how it was doing it. And even now you really can't get an explanation of what it's doing and how it's doing it. So the math is pretty obtuse, and so yes, it accounts for it, but maybe it's accounting for it because it's really just creating another formula that says one thing, but it's really just a formula that's accounting for the fact that the sun precesses. Alright, anyway, So the next thing that came along was the idea that Einstein declared that there was a 2x increase in the gravity that light would be affected by. And now that was based on this equivalency principle that's really a sidebar, and really an unnecessary step to take, in my opinion, in terms of there's no reason to say that all acceleration is the same when you know that there's different ways to accelerate you or different ways to impose force on you. I can hit you with a water hose, or I could hit you with one stream of water, and one stream of water at a certain pressure could bore a hole right through you, where if I hit you with a bunch of little drops, it'll just push you gently in a direction. So we know that how you get accelerated is going to be very different depending on what's accelerating you. The point is that gravity is accelerating you with the raindrop idea. Little tiny pieces of energy are hitting a lot of you. Okay, so a lot of you is being pushed directly by the force, and then the rest of you is being pushed because, you know, once your head starts moving, that puts pressure on your neck, and that puts pressure on all the other parts to also move, because they're all tied to each other. So part of it is direct interaction with the raindrops, and then part of it's going to be the spread from one cell to another cell to another cell or atom inside your body. And if you were in a rocket, obviously it's quite different, that all of the energy has to go through your feet. All of the energy has to be transferred from pieces of you and through you, through cells, through the tide, the mechanism of your body. And so it is a different way to be accelerated. There's no reason to compare the two. Now the idea is that if we had a spaceship and we had a light clock and we shot light across the ship, so Einstein gets this part right in the sense that the understanding is that photons don't care about this thing moving. Now I would argue they do care, because unlike in the past, I think we can all know that a photon isn't one instantaneously created object that flies through space. Okay, that a photon has a frequency, and the frequency is really just quanta at a distance. And so a photon is created over a period of time. And you can kind of understand this, the intuition of this, by just understanding that all the other electromagnetic radiation is created by an antenna. Antennas make it. And that all you're really doing is shrinking the antenna. So when you go to the very high frequency, like, you know, you have radio waves would have a very tall antenna, and then for microwaves you get a very small antenna. You don't need more antenna, but you really can't use it, because any energy that goes this far up the antenna would already be behind in terms of its frequency. This distance would be useless, because the frequency forces you to release the objects within this distance. If you don't release your photon within this distance, this extra is of no value, because it will just make your signal out of phase. So it doesn't do you any good to have any energy waiting that long to get out of the antenna. And the real idea is that the speed of light is creating the photon, in the sense that it's just another antenna. So this would be microwaves, and light is very tiny, so it has a very tiny antenna. And so it's just a row of atoms, and the electricity goes through the row of atoms, and each one of the atoms produces a little bit. And obviously it'll take a little time for this little bit to be released, and it takes a little more time for this one to be released, and it takes a little more time for this one to be released. And these two distances will be proportional. The frequency will be proportional to the out of alignment, which means this would be the polarization and this would be the frequency. And that's perfectly consistent with every experimental result known to man, and so it can be really just understood that way. It's just a smaller antenna, smaller antenna, smaller. You want X-rays, you get even smaller antenna. Very few atoms involved, and very little polarization. So that's how photons are produced. They are composite objects. So even in Einstein's light experiment, it's too much of a generalization. It's too much of a simplification, because it has this idea that I can shoot a whole photon in one constant of time. Like in 1t, I made a photon. When it takes more than 1t, it takes numerous t's, units of time, for the photon to even be produced. So in those units of time, if I'm moving this half the speed of light, I'm increasing the polarization of the light. I'm doubling it, essentially. And so I might not make the light visible anyway, or usable, because now I've increased the spread of the bits, and now the bits can't hit another surface with any continuity. And it's going to hit atoms that are very far from each other, and therefore not be able to reconstruct through the crystal process a new piece of electricity, like a piezoelectric effect. Photons are kind of created by hitting a crystal of metal with a certain amount of energy and a certain amount of time, and then the crystal creates an electric current. That would be a simplification, but that's the basic mechanism, and our light functions that way. So anyway, the spaceship argument is that, let's say if we did think of this photon as one unit, the fact is it would travel straight. It wouldn't have two momentums. It would travel the speed of light away from the emitter, and the motion of the emitter would be irrelevant. So as the rocket ship moves up, the target that was here, okay, is now going to be way up here, and your beam of light is progressing across your ship here. And so it's obviously not going to be able to hit the target. Okay, it's going to miss the target. And if you were moving with the target, that is, you were an observer inside here looking at the target, you'd say, hey, that light bent down. That's what you'd see. Now what you'd see doesn't have anything to do, you can understand, it doesn't have anything to do with the reality, because what you're seeing is frame rates and moments of time. The light really did move straight, but this is what you saw because of your frame rate problem. Alright, you're seeing it badly. Okay, you're seeing ghosts. And the reality was the light went straight across, okay, and the fact is that you moved away. And as you moved away, you saw the photons, the movement of the photon incorrectly. That is, if you could even see. You know, we're presuming you have a fog in here and you can see the laser beam and all kinds of assumptions that are made that won't be the reality. But the truth is that the joke is that this breaks Einstein's own theory, because you could use this as a speedometer to tell you exactly how fast you're going. You just see how much the light bent. So in a sense, his own thought experiment undoes his own theory by saying, you know, because part of his theory is that you can't tell who's moving and who's not moving. Well, the light clock will tell you who's moving and who's not moving. If two ships are going back and forth here, the one where the light goes straight across is obviously moving less than the one that the light bends in. So that would be an easy way to tell how fast you're absolutely going. So, not dealt with by Einstein in this book anyway, as far as I could tell. Didn't think of it, I guess. So anyway, so the whole reason why Einstein decided to make this equivalency principle, or this 2x increase in how much light is bent by gravity. So nothing else is bent, okay, just light. Nothing else, not magnetism, not gravity itself, not anything else is bent 2x. Just this one kind of energy in the universe. And again, we know they're all the same thing. Come on, they all move the same speed. They all are quantized in terms of their effects on things. There's just no reason to think light is a special form of force in the universe. It's the same stuff as the virtual photons they use to explain quantum mechanics, and the same stuff that gravity is, because it's all moving the same speed. So it's just silly not to go where the facts are pointing so obviously, and to say I'm going to deny that truth because of some, you know, interpretation of a thought experiment. So anyway, so Einstein basically decided he has to make the light on the Earth look like light on the spaceship. Now, even though the Earth is doing something fundamentally different, which is the gravity, the spaceship just has one rocket, right? So there's only one source of acceleration here, our movement, where on Earth the acceleration is kind of deceptive. You have the force of gravity that's pushing you down, that you're completely unaware of, and the one that you're really noticing is the fact that the Earth is pushing you up. So you have two sources, one counterbalancing the other, in the sense that one's pushing you down, moving you down, and the other is pushing you up. Now you think, okay, that means I'm not moving. But the truth is both accelerations are always affecting you. That's why you feel it. That's why you feel the ground and feel it on your butt when you're sitting, is because it's active. These are both active forces. They don't just cancel each other out. They actually force you to, your atoms have to actually move down, and then your atoms have to actually move back up. So they're constantly moving back and forth, which means they're traveling an awful lot of distance, which means if you are moving on the surface of the Earth, you're moving a lot more distance than you think you are. So when the Earth is turning and we're all turning on the surface of the Earth, we think we're going a certain speed, 22 miles an hour, whatever it is. But the fact is we're going a lot faster than that, because we're like a basketball. It's going much faster than the basketball player. Our velocity has to account for all this extra distance we're traveling as we jiggle up and down on the surface of the Earth, as our parts do both motions. Our parts are doing both motions. And so that's why, when you go to the time dilation fact, that people think the satellite has to be adjusted because it's time dilated. It's going 22,000 miles an hour or some number like that, and we think we're going slow and it's going fast. But the truth is, because we're near the Earth, we're jiggling at a very high frequency, okay, in heavy gravity. It's jiggling in very low gravity. So there's very little added to its velocity by the extra distance it's traveling, and there's a lot added to our distance. So we're actually the ones going faster. So anyway, and why speed has any relevance, I'll get to also. So let's see, do I still need the spaceship? So so just understand that this is not a very good thought experiment. It's not a good reason to make gravity twice as effective. It's just because you want it to look the same. So he just wants light to look the same. He wants it to look like it bends, like it bent in the spaceship. So he wants these two things to look the same. And that's kind of a silly reason to create such an extreme weirdness. So nothing else, electrons, protons, atoms, planets, nothing else is twice affected by gravity except the thing moving the fastest of all the stuff in the universe. And only one variety of this stuff. Again, magnetism isn't affected. Gravity isn't affected. All these other things aren't bent by gravity. Just light. All right. So this was the second tier of Einstein's fame. What built it, what made Einstein seem credible. And this is the Eddington experiment. So Eddington, a believer in Einstein, one of the only ones on Earth who understood and believed, persuaded the British institution to spend a bunch of money to do this experiment to basically prove Einstein wrong. And so he was kind of a subversive character in a way. He's kind of a cheater, in the fact that I think he was basically lying to the institution that was paying for the experiment in terms of what his intent was. But regardless, the idea is that we could measure this 2x difference by observing a star around the sun and seeing that the light from that star would be in this subtly different location, okay, because of the bending of this light. Okay, so we would see it, here instead of here. Okay, and it's this tiny, tiny difference. So I don't know how to make the comparison. So it's like seeing the difference in one person's hair, a hair worth of thickness difference in somebody's position when they're 10 meters away. It's you need a really, it's a very exact kind of thing. And the gravity out here is very weak. The gravity on the surface of the sun is only 8 times what it is on Earth. So it's only 80 meters per second. That's all it is. This is, the sun's made out of hydrogen, helium, light stuff. It's not very dense, so the gravity isn't all that impressive. And the fact is, you have to get outside the sun's corona. That means you have to get a full radius outside the sun to be able to do the experiment, because this is all kind of noisy, full of crap that will bend light. I'll get into that. So to have any legitimacy, you have to do the experiment on stars that end up pretty far away, actually, from the sun. So now this is really weak gravity that you're trying to do this in. It's one quarter of what it is on the surface, and you know, twice the distance. Yeah, so you know, it's you know, only 20 meters per second. It's not much, you know, not that much, only twice as much as the gravity on Earth, on the surface of the Earth. So anyway, so it's a marginal experiment to be able to see this little tiny difference. And so Eddington did the experiment. It says right in his journal, I wouldn't stake my life on these results. He was hoping to get 10,000 stars on his photographic plates. He got something over 1,000. So 10% of the quality he was hoping for. Lots of problems in doing the experiment. These are all time-lapse photos. Now, you know, in one case they're moving the telescope with the sun. I think in the other case they didn't move the telescope. Obviously these are kind of complex things to be doing back in 1918. You know, being able to track the movement. We don't really see any of the evidence, and it's, you know, it's a tiny difference, and very hard to do even under perfect conditions, far less than perfect. But anyway, the declaration is that he found the necessary 1.74 instead of the expected 92 or whatever, 80, let's just say 80 something. So regular gravity would be 81 number, double gravity would be this 174 number, with ever little tiny changes for some mathematical reason. So anyway, so it was declared he had found the bigger number. Now I would argue they didn't even find this number, frankly. Okay, let alone this number. I'd say the experiment is that bad, and all of them have been that bad. But anyway, we'll just venture on to explaining that, okay, the experiment, so the experiment back in 1918 was done with a 12-foot telescope with like at least a 12-inch hunk of glass, kind of a nice piece of hardware that dragged all the way to South America and went all the way to Africa. Not a minor piece of technology. Nobody's come close to matching that technology and doing the experiment a second time. So it's never been verified with better technology. You know, and the more modern the experiment, the weaker the technology gets, the lazier it gets. You know, you're using, you know, 25 megapixel camera, okay, 5-inch lens. You know, you're getting 50 stars in your view. You know, compared to 10,000. You know, the technology is so much weaker. And the big point is that we've had space technologies, thousands of satellites now in space with very nice cameras on them, and the resolution in space is 400 times better. So that means you need 400 times. You know, like if I had a 12-inch lens on Earth, I can use a you know, 1-inch lens in space. I mean, it's 400 times better resolution when you're looking at space objects. Just a huge advantage in space. I mean, you can't even. How can I exaggerate? I mean, it's 400 times better resolution, 400 times more pixels, 400 times better resolution. It's like going from a 10 megapixel camera to a 10,000 megapixel camera or something. It's huge. And it's never been done from space. So even though you don't need an eclipse, you know, anytime you want to, you can look at the sun and look right next to it and see a star and watch it, what it's doing. You know, anytime they want to do the experiment, they can do it. You know, perfect sight, perfect vision, and 400 times better resolution. And yet we don't have any evidence it's even been attempted. And that should say something to the world of science, that there's something wrong with that picture, something very wrong with that picture. Simple experiment, really. It would cost hundreds of dollars, you know, of satellite time. I mean, even if we said a satellite was worth $2,000 an hour, I mean, it's all it's going to take to do the experiment is an hour of satellite time, and it's never been done. All right, so anyway, New York Times headline: Einstein writes, Einstein becomes an international hero. So then everything he says all of a sudden is credible. So now we have this whole thing invented of space-time. And so the remaining feature, okay, so this stuff doesn't really have anything to do with space-time, right? I mean, the fact that light is bent is irrelevant to space-time, okay? It's irrelevant to this idea that time is a fourth dimension. You know, there's no room for 4 dimensions. There's only room for 3. Dimensions are defined by a perpendicular angle. Okay, the 3 dimensions have a 90-degree angle to each other. Okay, so there's only room for those 3 90-degree angles, and once you're done those 3, you're done making dimensions. Okay, you're all out of spatial dimensions. There's no room for any other dimensions. So it's an abuse of language to call it a 4th dimension. It can't in any way be connected to the 3 physical dimensions. But just this idea that somehow distance, okay, is time. Well, obviously that's true. So, you know, we know that if the speed of light is going to decide how soon something knows something else happened, that is significant, because, you know, an event is going to happen depending on how close you are. The further away you are, the event happened at a different time than if you're closer. But that's, again, your perception only. And your interaction. It doesn't have anything to do with what actually happens. All right, so the other component of Einstein is this connection between space and time. So the idea is that see, Einstein's part, the kernel of it is correct in my opinion. There's nothing I would be opposed to. This idea that light is the universal timekeeper. So how much time it takes for something to get from one place to another place at the speed of light is the timekeeper. That'll tell you that's a notch of time, is that notch of distance. And sort of the argument is that if you're moving very fast, that what's happening is that you're slowing down. So it's not that you live longer. It's not like I can go fast and I can live more life experiences. The point is that you have a certain number of experiences and they just fit on your distance line. So if you go fast, you're covering more distance, but the notches on your ruler are bigger. So, you know, 10 years is 10 years, 20 years is 20 years. And it's just if you're not moving fast, the notches are much closer together. And so all you're doing is changing how big the notches are. So you're not going to live longer by moving faster. You're going to live slower, you know, a lot slower. So that's sort of the idea, is that somehow our metabolism would slow down. And so to make the fact that I could shoot you know, say if I had a flashlight and I was going to shoot light out of the flashlight, what Einstein's really saying is if I'm moving half the speed of light and I shine the light, it will look like to me that the light left at the speed of light, because, you know, that's going away from me. But the truth is that will only happen because what used to be 1 year of time will now be 10,000 years of time. So I will be watching, the rest of the universe will be zooming by, you know, I mean, in the sense that I'm going so fast, the universe will be just flying by me like a blur. I'm going so fast, and time is going by, and so I'm really going to watch the time difference for the half speed of light thing to look like, okay, it was actually going the speed of light. So for it to look that way, I have to perceive reality at, you know, substantially half the speed, more than that. I mean, you know, I'm not going to try to do the get all of the percentage numbers correct, but the point would be is that if you're going half the speed of light, you're going to just be moving, like everything you're doing is going to be real slow based on Earth time. You know, the Earth ages, blows up, falls into the sun, does all kinds of things while you're waiting for the beam of light you shine with your flashlight to actually look like it's going the speed of light. It's because it's going to take a while for that to happen, a long while. All right. So there's no reason to believe there's actually any that any of this stuff actually happens. Now the catch is that the way we count time is with these different kinds of clocks, and we can use crystals and we can use different things. And the fact is that radioactive decay is kind of reliable. So when something is decaying, there's a certain amount of radioactive elements. They will produce a certain rate of decay, and that rate will be pretty consistent. And so we can use that rate as a timekeeper. You know, it'll tell really good time when we average that decay rate. And so we can get a pretty small unit of time because it decays, you know, at a very fast rate. There's always something popping out of it every picosecond or whatever. Every billionth of a second there's something popping out of it. So it gives us lots of little notches to use, and when we generalize those notches over a longer period of time, we can get a very reliable, you know, maybe it's ticking at 1/trillionth of a second. We're going to average it to a billionth of a second. So it'll give us a very good reliable tick for billionth of a second, billionth of a second, billionth of a second, based on the fact that the decay has a reliable rate, consistent rate, if you don't change its environment. Obviously I can change its environment. I could put another radioactive isotope next to it and I can cause this rate to change. So I can affect the rate with radiation. So just like what we do in power plants is we take a whole bunch of radioactive material and put it close to each other, and that increases its decay rate. So it decays quicker by consolidating it. So it's capable of increasing its decay rate if I increase its exposure to energy. And we could argue that velocity is an increase in exposure to energy. And so there would be it's not unnatural or unexpected that you might think that if I move a decaying particle, that I will in fact slow down its decay rate, okay, and change its decay rate. So again, the irony is that the decaying clock on Earth, the decaying substance, is actually decaying faster. These clocks on Earth are the ones that are being slowed down, and the ones in space are the ones going too fast. So, you know, that's the irony. I believe that's the way it works. And the trick is that because the one on Earth is the one still jiggling in this stronger gravity, so it's in fact, you know, traveling more distance, which means it's exposed to more force interactions, which means it should be decaying faster because it's moving faster. Decaying faster. I think I have that backwards actually. Well, anyway, the decay rate would change based on movement. So you could argue, let's say decay, so there's another way to argue it. I'll argue this argument. Let's say that what decides whether an element decays is a circumstantial event, you know, something that happens from the external world. And the external world, the event could be that you have to get hit by a force in both directions at exactly the same time. And so when you have that unique event, you know, that event that doesn't happen, that happens, you know, at a regular interval, that's when you cause this thing to decay. So there's an environmental circumstance that creates decay. you know, that the thing doesn't decay based on some internal clock. It decays based on an external circumstance that just happens to be probabilistically rare. And so stuff can last 10,000 years because it takes 10,000 years for you to, you know, have this event happen, this unique event, or this, again, not unique, this improbable event. And so you could argue that if I move the isotope, that the more I move it, the less possible that coincidental event becomes, because now I've made it less likely it gets hit by a force from this direction. It's moving this way. And I make it more likely it gets hit from this. So now I've made uneven events more likely, not even events. So the probability of the circumstance where something hits it at the same time is now reduced, because I've reduced the number of possible circumstances where this one is hitting. So even though I've increased the number here, I've decreased the number here, and this decrease will tell you what the probability of a coincidental, both of them hitting at the same time event. So even if it worked the other way and this one was less and this one was more, it just doesn't matter. The fact that I've imbalanced it means that I've reduced the probability of the matching event. Just like if I had two sets of dice and I reduced the number, you know, one set to 5 dice and the other set had 10 dice, now having matching would be less probable. I've reduced the probability in half of them having matching components in terms of the permutation. So you can understand that there's reasons why decay might be retarded by velocity. So velocity retards decay by making an event less probable. And so, but this is another piece of evidence. It's just another, you could argue, well, maybe it's just a coincidence, an unfortunate coincidence, that atomic decay does fit Einstein's theory that motion retards the aging of a decaying molecule. Now, the other piece of evidence they use is muons coming from the atmosphere. And, you know, this one's kind of easy to say, come on, you're really stretching. So the idea is they have an object that comes from space that's moving very fast, and that's the whole point. It's moving very fast. So they can be going 20 miles an hour, or, you know, I'm just making that up, or they can go 40. There's variation in how fast they can go. And the point is they say, well, the ones going 40 miles an hour last longer. Well, you could sort of understand why they last longer if they're getting degraded in their speed as they travel through substance. So as they travel through the atmosphere, their speed degrades. Well, you could understand that obviously the one that started off at 20 miles an hour isn't going to be able to go as far as the one that started off going 40 miles an hour. You know, if you're plowing through a fog, or, you know, even swimming through water, or, you know, like a torpedo. If I start the torpedo at 20 miles an hour, it'll have a certain distance it can go, okay, if it doesn't have a motor. And if it's 40 miles an hour, obviously the distance is further. And so they take that to mean that it lasted longer. Okay, the fact that it, you know, the fact that there's a correlation between how fast it starts at and the fact that it lasts longer, well, of course it lasted longer. So, you know, they have a device they call a scintillator, and they get a little photon when it finally dies, when its velocity stops. Well, its velocity doesn't really stop. It just becomes capable of hitting an object and being absorbed by it. And when it's absorbed, the energy is released as a photon. Now, even all that's kind of suspect, right? Because I would argue you can't make photons out of anything less than an ion. You have to have atomic structure to release photons. You can't just have an electron or a proton or something. You got to hit an atom. That's why it's a scintillator. It's actually a material, plastic. And they let the muons go through, and they say, this one decayed because it created a photon. Well, it created a photon because it hit atoms, you know, not because it hit, you know, an electron. But anyway, to take that a step further, I'm just saying, obviously measuring, so to say that this is time dilated, okay, in its decay, well, first off, it's not decaying like radioactive decay. It's just decaying in that it's losing velocity. with distance. And so it's a whole different kind of thing. And but anyway, but they do use this as evidence, saying that, see, it lived longer, okay, because it was moving faster. And so they're just, and clearly it's more durable if it's faster. The bullet goes deeper into the jello if I shoot the bullet with a stronger amount of gunpowder in it. So it's, it's a very weak argument, but they pile that one in too. So the point is, I'm not saying this isn't any evidence. This is some reason to believe, but it's a very weak reasoning. I mean, again, as I pointed out, there's lots of ways to understand that, okay, what this seems like thing isn't quite what it looks like, okay, and measuring how long something that can move at a variable speed, and then saying, that I've changed, that somehow they started off all the same when they didn't, and then to say that some lived longer because they were going faster when living longer just has to do with surviving distance through substance. And, that's a terrible attempt at a correlation. It doesn't match at all. Alright, so maybe I'll take a break and think. So those are the 3 bits. So you have the precession of Mercury. Einstein got a win for that. And then you have the bending of light 2x, which I'd say is such a mixed bag. I mean, it comes with all kinds of baggage. And yeah, I probably should get into some of the galactic stuff and the idea of how much gravity there is in the universe, how much gravity it's even possible to create this lensing effect in a more dramatic way where you might be able to see it. And certainly I can point out how bad the gravitational lensing images are from space. But anyway, so you have this idea of the 2x guess, or the 2x prediction. And yeah, so I can go into the other experiments that have to do with light. So there's other experiments, using radio waves and other sources, where they say they have gravitational lensing, where they've proven that light was bent by gravity. And the problem with all of these so all the other experiments, that claim light being bent, the problem is they're measuring sources. So there's a source, say, behind something, and the source shoots light in all of these places, obviously, a radiation. The radiation goes everywhere. And some of it goes right across the surface and is bent. And the idea, though, is that when you go across the surface of a sun, as I pointed out, we know the suns are covered in energy. So the corona of the sun is dense with electrons and protons and ions and charged particles. And so you would perfectly expect that you would have light that could take this short path. So what they're basically saying is how does the light take this shorter path? How, if it wasn't gravity that bent the light? And clearly, scatter would do it. Scatter would be sending light here, 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 to all these locations. And yes, some of those locations will be shorter lines. And you'll see something that you shouldn't be able to see, is really the point. So the radio source is behind this. You can't see it from here, and yet we're detecting it. And so we think, well, how does it do that? I mean, it can't get through the source, the blocking thing. So how can we possibly be seeing something or hearing something that's blocked by another object? And there are clearly easy ways to do that through scatter. Scatter will provide you the shorter path, and it'll provide every location with that shorter path. They'll all be able to see it, sooner than they expect. And so I guess the opposite would be the version where you can see it, and the light, the energy is bent. I don't think that could ever be a shorter path. So it's really always has to be behind objects behind other objects. So anyway, so yes, it's another piece of evidence that, oh, look, light doesn't go where we expected it to. But in a sense, the expectation that you could shoot light through it's like even a fog. A fog will do the same thing. You know, you could put something behind another object, a light, headlight, behind a brick wall. And if I make it foggy, you'll see the light. Where if it's not foggy, you don't see the light. You know, because the light, the brick wall is here, the light source is here, you're here, and you can sort of understand that, yeah, the fog will light up here. And now I'll be able to see those photons. You know, and it's a similar thing. The scatter is providing you information. The fact that the light's scattering off the water molecules means that they have a path to get to you. Okay, where they couldn't get to you without that reflection. So the sun is basically covered with a bunch of little mirrors, is the argument, and you know, and the little mirrors, some of them are going to be the right angle to get to you. So all of the other evidence is in that form where you'd say, well, you're saying it's lensing, but there's no reason to think it is. There's no reason to think gravity did the bending of this light, and there's every reason to think you hit a bunch of plasma, a bunch of fog, and that's why we're seeing the photons. You can't, when you're seeing the light, you can't tell, you know, light that was bent by gravity from light that was bent by scatter. I mean, they're not, the photons won't give you any revealing information to tell you, oh, I can tell the difference. It's going to be the same photon. Alright, so maybe take a break and see if there's anything else I need to go over. Alright, should be back. Yes. Alright, so the other thing I wanted to go over just real somewhat briefly. So I sort of pointed out that we don't really have a great source locally in the sun, because, you know, the 8 times as much gravity as on Earth isn't very much, and then out here it's, you know, it's only 2x times the Earth's gravity on the surface. Not very good for viewing this gravitational lensing thing. So in space, you know, we have galaxies, you know, these things with the swirly arms, a lot of them anyway. Well, I drew that poorly because it all swirls in one direction, but anyway. And the idea is there's some really heavy mass in here. They say there's black holes in there. And everything's orbiting the black hole. Now, what you will see with gravities is, you know, with galaxies, is that there's a symmetry usually. There's just as much mass on this side, okay, as there is on this side. Unlike a solar system that has stuff here and here and here, very sparse, okay, and sometimes all the stuff is on one side, you know, not a very even system at all because there's so little mass out here, okay, compared to a galaxy. So a galaxy really is, as you could understand, that it's made, probably, this would be a reasonable enough theory, is that it's 2 stars orbiting around each other's gravity. So they're just basically, you know, a system that starts off with 2 stars, 2 heavy things, okay, and those 2 heavy things are generating, you know, the system, and it kind of explains why, you know, everything just sort of drags behind, you know, the position of those 2 stars, and that everything is just a ghost of their previous condition. And so, but you can sort of understand that the gravity is more like this gravity. These 2 things are orbiting around each other, and these 2 things are orbiting around each other, almost like you get rid of the sun and you put another Earth on the other side. So, you know, right through the sun, you put another Earth on that other side. And if they're heavy enough and moving the right velocity, those 2 objects will just orbit around each other. You know, they'll just keep going around and around and around that center point. You know, this line will always stay the same, and they'll just go around and around and around as these 2 objects. So there's mechanics that are possible, that gravity makes possible, where you don't need a heavy mass in the middle. And I'd say galaxies are obviously don't need a heavy mass in the middle, because the mass of these objects in themselves is enough to keep them together. Now, the other part is whether they're falling apart or getting smaller. I would argue that quasars are essentially old galaxies, viewed when they're in their younger state, and that billions of years ago, galaxies were heavier and smaller, more mass and smaller location, and that galaxies are in fact falling apart. And if they're falling apart, you'd have every expectation that pieces of them on the outside would be moving too fast or too slow, that they're perfectly legal to be moving the wrong speed, especially too fast, because that means they're leaving the system. And that could reverse if you just change gravity. Okay, if you change how much energy there is in space, the bending factor, if you want to still use your vernacular, I just changed the bending factor. What the hell happened to the camera? It's a little bit not quite where I need it to be. No, that's not quite where I need it to be either. Anyway, then I could make the object small again. So if gravity was just this idea that, you know, energy goes into systems, they get smaller, you know, the gravity gets stronger, the system gets smaller. As the system gets smaller, it absorbed energy from the system, from space, and so space gets weaker. And when space gets weaker, then the system spreads out again, and then it contracts, and then it expands and contracts. And that's sort of what we see, in the sense that galaxies have somewhat consistency to them. Now, there are some oddly shaped galaxies, I suppose, but you know, we don't get to see too many of those pictures. But what we really don't see is the, you know, the idea that you have a thing in the center and everything ends up going flat. So like the solar system, you could assume that the solar system started off very unflat. That is, there was stuff orbiting this way and stuff orbiting all kinds of ways. And it's just something that happens over time with these systems. So it's like if you threw marbles into a gravity well, you know, you made a fake gravity well and you throw marbles going both ways. What you'll find is whatever marbles have the most velocity and momentum, total momentum, okay, this group of marbles or this group of marbles, whatever one has the greater total momentum will end up winning in the end, and all the marbles that are left after a minute or so, or whatever, 20 seconds. So the marbles start off going this way, and it'll end up, you know, at some point they're going to be just going one way. They're all going to be going the same way. So you can kind of tell the age of something based on how they're all going one way. And so you can tell, like, our solar system had to be this kind of old, because obviously everything's going the same way, and the same thing happens to this idea of things being off the plane. Everything will bend to one plane. So as one plane gets denser and denser, so one plane just happens to have more stuff on it, that plane will inevitably eat all the weaker planes. You know, they'll all be compelled to move towards that plane, slowly but surely orbit their way up. So the flatter and flatter a solar system gets, or a galaxy gets, it sort of means it's older, because it's flattened out. Now, it depends on how galaxies are formed. Like I said, if they're made out of binary stars, you know, two stars are two, you could even say two neutron stars, you know, two very heavy stars circulating around each other and breaking apart, and, you know, the new stars are being formed going out because it's falling apart. You can't understand that that would create the galaxy in one plane. This would be the plane that those two stars are orbiting in. And so that's why they tend to go flat. All right, so finding heavy gravity in the universe isn't that easy if I'm right, and that everything isn't dependent on a big heavy thing in the middle and then it orbits around. If the big universe, the galaxies especially, are dependent on a different scenario where two objects are rotating around each other, and that all the objects that spread out of them, that is all the little bits they make, aren't really orbiting around those two objects, they're really orbiting around each other. The mass of this collection is orbiting around the mass of that collection. And this stuff in the middle isn't playing as nearly as strong a role. It's not all about the sun's gravity. It's about the fact that we have the Earth on the other side. Okay, and that Earth has a, you know, to be at the Earth's distances, these distances wouldn't work. So you'd have to make the Earth much heavier, of course. But the idea is sound, that two objects will do this. They'll just object two pieces of dust. If you have them at the right velocity and the right distance, you can make two pieces of dust, you know, just orbit around each other, create a binary system. So galaxies are just layers of a binary system. Well, anyway, so there's no reason to think they have some sort of insane amount of gravity that they're creating, and that they're producing some sort of massive gravitational effect. You know, the galaxy's here, and it's got some huge gravity at this location or something. There's no reason to think that's true. All right, so the argument is they say they have images from the Hubble that essentially are this gravitational lensing, that some distance from something, there's this huge amount of gravity, and the light traveled through it, and this is hundreds of light years, hundreds of thousands of light years across, 100,000 light years, you know, huge giant lens. And the light takes, you know, many thousands of years to travel through the gravity to be bent. So it's bent obviously on an arc. And it gets to us, and we see these funky images from space. Now the problem is most of the images have horrible symmetry. That is, the curves are like this, and there's a curve here, and you know, then they have curves that are like a little piece this way, and then there's a little piece this way, and then there's a little piece this way, and they don't match at all. There's no symmetry. And gravity, strong gravity, creates really symmetrical objects, just like all the big gas planets are really nicely spherical. Now they're all spinning, so they all have a little bit of a bulge around the middle, but the point is the surface is dead flat. You know, surface of the moon, surface of the earth, you know, consider, I mean, Mount Everest is just a tiny little blip compared to this 4,000 mile difference, or whatever it is, 8,000, radius is 4, well, something, 4,000 I think it is for the diameter. Well, anyway, you know, you're talking about, you know, 1/4000th. You know, it's a tiny blip on the surface of the Earth. So things tend to go very, very, very mathematically perfect. You know, they get very spherical, very smooth on their surface the heavier they get. So this gravity, it's supposed to be very strong, should be very symmetrical in these locations. And so there's no reason that they would have these blotches of perfect gravity for a perfect little arc, but then the arc stops and it comes out in another place, and the gravity is very uneven. There's just no viable explanation for that kind of lack of perfection, because strong gravity would demand it. It would force, everything in this universe would be forced to be obedient to that strong gravity. So they make up this excuse that there's little clumps of dark matter here and clumps of dark matter in different locations, and that's screwing up the perfect mathematics. And you know, this seems like a desperate effort to recoup a theory that just doesn't work. It doesn't make sense. So there's a ton of places where we know there's really strong gravity, and yet we don't see the rest of the universe being lensed into it. So there's places in the universe that we say there's a black hole, and we know there's stuff orbiting. And yet, when we look in those spaces, we don't see the rest of the universe. We don't see a star from over here being bent. We don't see stars over here being bent, and all kinds of crap flying in here. So the universe isn't like a fog. It isn't full of light being bent all over the place, and we're seeing a ton of fake images all over the place. And that really would be the consequence if lensing was a fact, and that their theory of where the mass is in the universe was a fact. There should be a lot of scatter, and light shouldn't be able to get 15 billion light years across the universe to get to us in any kind of rational condition. All of it should be all kinds of messed up. You know, we should be seeing light from places that are erroneous to where the actual objects are, because of the fact that the light has gone through this gauntlet of gravitational lensing. And again, twice the effect of all other objects in the universe. It's still just there's just no way to understand why the magical photon is 2x, okay, affected by gravity, bent twice as much. You know, everything else bends this much, light bends twice as much, and there's just no reason to think why. Why is light special? Why is light not like magnetism and the electric field and the gravitational field? Why is it so much different than these other things? These other things aren't bent at all, by the way. So they're not even bent 1x. But all the other stuff, electrons and protons, are bent this much. Why is light bent this much? There's just no good explanation for that. It just seems to stick out and say that probably isn't true, and unless you have really, really good evidence, you shouldn't necessarily draw that conclusion. And I guess I'm arguing the evidence is not very good. So all the galactic lensing images don't make much sense. The lens is the wrong shape, by the way. I mean, it's functioning exactly the opposite. A gravitational lens, creates a lot of bending near the center and very little bending out here. Not very good for creating a focus here. So it would only be good at taking light that was already coming at a wrong angle and fixing it. There's lots of reasons to doubt the theory and to doubt the effect. I could get into gravitational waves, which is a whole nother pile of mush, where they say two black holes crash into each other. They have a certain amount of mass, let's just say 3 and 3. Somehow they destroy some of that mass. When they crash into each other, they create a new thing. The new thing has a mass of 5, and it somehow gave away one of its masses, a ton of itself. And it turned that mass somehow into bent space that went flying through space. This bent space did. And it doesn't disturb any of these other planets. It doesn't push them all over the place, these other stars. They don't get no evidence of this wave affecting anything, because they sort of made it as passive as they could. They don't want to make it light radiation or gamma rays, or, it's not in any real form of radiation. It's in something called a bent space wave. And then they're going to detect that here on Earth. Now, again, they blame Einstein for this, and Einstein didn't say this was possible, but you could take this huge amount of energy out of a system, convert it into a bent space, and then vibrate a mirror on Earth. And I've really already explained why the whole LIGO interferometer thing is flawed theory, because there's no such thing as 2 equal beams in a beam splitter. There's no such thing as a mirror that reflects light from the same location each time. These are all misunderstandings of what you're really measuring with an interferometer, how accurate it actually is. You're really not measuring the wavelengths of light, you're measuring the spread of the beam of your laser. So they have a misunderstanding of what they're measuring and how accurate their device actually is. Yeah, it was never tested and blah 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 blah. Alright, so I think that's probably enough to cover it. So there's no such thing as a time dimension. There's just space. And the fact is that the forces move the speed of light, and matter can be pushed by a force, and it can move something up to the speed of the force, but it can't move faster than the force, obviously, because the matter is always being pushed. So wherever it goes, it was pushed there, and it can only be pushed by stuff going the speed of light. So therefore, of course, it can never go faster than the speed of light, because it can't be pushed any faster than the speed of the force. The force is the only speed there is. It doesn't matter once you've got it up to speed. It doesn't matter how much more force you pile up, because it's going as fast as the force, and the force can never catch up to it, so it can never apply more push. So it can't be pushed any faster, and that's just the simple truth. And you're not going to break that law of the truth. That fact is a fact, and I don't know why people imagine any other possibility. There's just no evidence of it, and it's just terrible not to understand the fundamental difference, that it's a push universe. Force pushes things. There's no pull, there's just an absence of push. So everything starts with push from everywhere, and the simple truth is that we can screw around with different things, putting different things in different arrangements, and we can kill some of the push going one way. So we can reduce the push here, a little less than push, here, and or we can put more push over here. We can add another arrow, and we can move stuff, but that's the only way you can move it, is to push it. And to eliminate the push, that will give the push every opportunity to push, and that's all there is. There really isn't anything else to the mechanism. The distance is all real. Everything is in a real position. Nothing is superimposed. Nothing. There's no theory where you can put electrons inside of electrons, inside of electrons, inside of electrons, inside of electrons, and create supergravity. There's no evidence of it existing. It's just all very weakly evidenced. That's the nicest thing you can say about their theory. Oh, it's very weakly evidenced. And everything else is going to be more derogatory, because why are you believing it? Why is it presumed to be the default? Something so poorly evidenced. Why is it you have to prove it wrong? Unlike them, they don't have to prove all the other alternative theories wrong. You know, they don't have to live by the same standards any other competing theory has to live by, which is very unfair. So anyway, enough of a video, I'd say, and so till the next time.